Hey everybody, now we're going to be discussing a topic known as linear optics. We talked for several DLs about how light behaves as a wave. One of the interesting things about light is that the wavelength tends to be extremely small, at least as compared to everyday objects. Because of this, we can figure out a lot of interesting results about the way light behaves without ever thinking about the fact that it's a wave. We're going to start by thinking about mirrors. Let's consider the simplest case of a flat mirror. Let's suppose we have a ray of light coming down and to the left and hitting the mirror. We want to know what direction this ray of light will travel after it reflects off the mirror. It turns out that it's fairly simple to figure out what happens. I'm going to draw a little something that will help us figure this out. This dotted black line is at a perfect right angle to the mirror itself. The direction that the light ray will travel after it bounces off the mirror is the direction such that the angle it makes with this perpendicular line is the same angle that the incoming light ray makes with the perpendicular line. This angle here and this angle here are the same. That's all you need to know when it comes to reflection. Even if the surface of the mirror is curved, this still works. All you have to do is draw a line that is perpendicular to the surface of the mirror, and then draw an outgoing ray that makes the same angle with that line as the incoming ray. Let's see how this works for spherical mirrors. This mirror is called spherical because if we continued it, it would make a perfect sphere. Let's suppose we have an object that's sitting right here. We want to know the path that the light rays leaving this object will take when they intersect with the mirror. Every spherical mirror has what's known as a focal point. The reason it's called a focal point is that every horizontal ray of light that reflects off the mirror will end up passing through the focal point. For example, let's consider the light ray that bounces off the top of this arrow and passes directly to the mirror horizontally. We want to know where that light ray goes. Well, we've already said that horizontal light rays always bounce off through the focal point. So the path of this light ray will look like this. I've told you that this is how horizontal light rays work, but let's just check to make sure this is right. Remember that the light ray that reflects off this mirror has to leave at the same angle with respect to the perpendicular that the incoming light ray does. To check this, let's actually draw a line that's perpendicular to the mirror at this point. This black line here points perpendicular to the surface of the mirror right here. Notice this light ray that's coming into the mirror is at the same angle to this black line as this light ray coming out of the mirror. It's perhaps not exactly the same, but that's just because my drawing isn't quite perfect. But you can see that they're certainly very close. Let's do two more light rays. The next light ray we're going to do is one that leaves the tip of this arrow and passes through the focal point before reflecting off the mirror. So we're following this ray of light here. What direction do you think it will travel after bouncing off the mirror? To figure this out, let's just draw the line that is perpendicular to the mirror here. Remember that the direction that the outgoing light ray travels will be such that the angle that it makes with this black line will be the same as the angle that the incoming ray of light makes. Let's draw that out. Notice an interesting fact about this light ray. It's traveling horizontally straight out. Let's think about why this is the case. Remember that we said that any light ray that travels towards the mirror horizontally will reflect in the direction of the focal point. So it probably doesn't surprise you that a light ray that travels to the mirror from the focal point reflects horizontally. It's just as if the light ray got turned around and sent back the other way. Let's draw one more light ray. When we're working with spherical mirrors, there are three primary light rays we like to draw in order to figure out what the image is going to look like. We've already drawn two of them. The first one is the light ray that travels directly horizontally and then bounces back through the focal point. The next one is a light ray that travels through the focal point and then bounces back horizontally. The third one is a light ray that passes through the center point of the mirror. Because this is a spherical mirror, there is a point that all points on the mirror are the same distance from, just as the center of a circle is the same distance from all points on the circle. Let's say the center of the circle is right here. Let's see what happens to a light ray that passes through this center point. What direction will the reflected ray go? It turns out this is the simplest one of all. Think about a circle. Now imagine drawing a line from the center of the circle to the edge of the circle. It turns out that if you do this, that line you draw will always be perpendicular to the circle itself. In the context of the light ray, this means that the light ray will just bounce back the same direction that it came. If I had drawn this well, all three of these light rays would converge on a single point. This point is where the image of the object will appear. Let's do the same exact thing, but for a convex mirror. This is our object here. Our focal point for this mirror is back here, and the center point is back here. Notice immediately there's a difference between this and the concave case. Because the mirror is between the object and the focal point, the light ray will never actually pass through the focal point or through the center. Instead, we will draw light rays that would pass through these points if the mirror was not there. But of course, since the mirror is there, the light ray will reflect off of it. Let's draw the same three rays. The first ray is the line that would pass through the focal point if the mirror was not there. Just as with the concave mirror, this light ray will be reflected horizontally. Our second light ray is one that travels horizontally towards the mirror. As with the concave case, this light ray will be reflected as though it was coming from the focal point. Of course, this light ray is not actually coming from the focal point because the focal point is behind the mirror. Instead, it's coming from the direction of the focal point. Here we have the horizontal ray coming in and this reflected light ray going out. If we continue this light ray backwards past the mirror, it would end up at the focal point. The last light ray is the one that travels directly towards the center of the mirror. As with the concave case, this light ray will just be reflected back in the exact same direction that it came from. I know this diagram is looking kind of busy, so let's just take a step back and make sure we know what's going on. There are three light rays in play here. They're bouncing off the mirror at three places, here, here, and here. This top light ray is traveling horizontally from the object and then traveling off in this direction as though it was coming from the focal point. This light ray right here is traveling from the object towards the center of the mirror and then bouncing back in the exact same direction that it came. The light ray that bounces off right here is traveling towards the focal point of the mirror and then reflecting off the mirror horizontally. When we were dealing with concave mirrors, there was a point where all of the light rays should converge. However, this is not the case with convex mirrors. While concave mirrors reflect light rays inwards, convex mirrors reflect light rays outwards. To find out where the image is for this mirror, we need to imagine that these reflected light rays were continued backwards behind the mirror. Remember, these light rays are not actually traveling behind the mirror. However, if we were standing over here looking at the mirror, this is the location that our eyes would think that all these light rays were coming from, even if they weren't actually ever passing through that point. To find this point, let's just imagine tracing these reflected lines back behind the mirror and see where they converge. If we trace the reflected light rays back behind the mirror, they all converge on this point. This is the location of the image in the mirror. In other words, if we were looking at the mirror from this side, our eyes would perceive that the reflected object was right here. It's just like when you're looking at yourself in a flat mirror. The image of yourself that you're seeing appears to be behind the mirror looking at you. It's the same thing here. The techniques that we're using here is known as ray tracing. When you're working on a problem with a spherical mirror, you always want to draw the same three primary rays. Those rays are the rays that travel in the direction of the focal point before reflecting off the mirror, the ray that travels horizontally from the object to the mirror, and the ray that travels in the direction of the center point before reflecting off the mirror. It can be very tricky to get these ray tracing diagrams exactly perfect, as we saw with my first example with the concave mirror. So don't worry about everything lining up exactly perfectly. As long as it's clear that you know which direction your rays should be traveling after bouncing off the mirror, you're totally fine. Let's take a minute to look at some equations that we can use to determine the location of these images. These are the two main equations that matter when we're thinking about mirrors. This first equation is called the mirror equation, and this second equation is called the magnification equation. Let's take a moment to see what they mean. In these equations, I stands for image, O stands for object, and F stands for focal point. However, sometimes these numbers will be positive, and sometimes they'll be negative. So let's take a moment to figure out which is which. By convention, the location of the object, O, is always positive. You can then determine the sign of I and F by asking yourself if they're on the same side of the mirror as the object or on the opposite side. For example, let's consider a case that we saw previously. We have this convex mirror and this object. As we said, the distance to the object will always be positive. But what about F, the distance to the focal point? Well, we know that for convex mirrors, the focal point is on this side of the mirror. So since it's on the opposite side of the mirror from the object, F will be negative. We expect that the image will appear over here, and therefore its distance will be negative. But if we knew the location of the object, and we knew the location of the focal point, we could solve this equation to determine the location of the image. If the number that we got out was negative, then we know that the image would have formed behind the mirror. And if the number that we got out was positive, we know that the image would have formed in front of the mirror. Now consider the concave case. The location of the object is still positive. However, now the focal point is on the same side of the mirror as the object itself, and so F will be positive. I, the location of the image, could be positive or negative. We don't know for sure, but we could always solve this equation to find out. If I was positive, then the location of the image would be on this side of the mirror. And if I was negative, then the location of the image would be on this side of the mirror. The second equation is called the magnification equation. It just tells us how large the image of the object appears as compared to the object itself. For example, if the image was twice as large as the object, then the magnification would be equal to 2. However, magnification can be positive or negative. A negative magnification does not necessarily mean that the image is smaller than the object. A negative magnification just means that the image itself will be upside down as compared to the object. However, it can still be larger or smaller than the object. A magnification of plus or minus 1 means that the image is the exact same size as the object. For plus 1, the image would be right side up, where for minus 1, the image would be upside down. We can find this magnification two ways. We can either take the height of the image and divide it by the height of the object, or we can take the location of the image, divide by the location of the object, and then add a negative sign. Let's do a quick example for a concave mirror. We have a concave mirror here that has a focal length of 5 centimeters. We place an object 7 centimeters away from the mirror. We want to know where the image will appear and its magnification. Let's start by finding the location of the image. To do that, we just need to plug our numbers into the mirror equation. I is the distance to the image and is what we're trying to find. O is the location of the object. F is the distance to the focal point. For a concave mirror, the focal point is on the same side of the mirror as the object, and so F will be positive. Let's now solve this equation for I. There we go. The location of our image is 17.5 centimeters. Because this number is positive, we know that the image will appear on the same side of the mirror as the object. If this object is 7 centimeters away from the mirror, 17.5 centimeters will be somewhere out here. Now we want to know the magnification of this image. To find this, we just need to plug the distance to the image and the distance to the object into our magnification equation. Let's do that here. Dividing 17.5 by 7 and putting a negative sign here, as required by the equation, gives us negative 2.5. The fact that this number is negative means that the image will be upside down as compared to the object. And 2.5 means that the image will be 2.5 times the size of the object. If we were to draw what the image should look like on this diagram, it would look something like this. The image is 17.5 centimeters away from the mirror. It is upside down, and it is 2.5 times larger than the object. I know there was a lot of information in this video, and you might have found some of it a little challenging to follow. You are, of course, always welcome to rewatch this video as many times as you like. However, there are also a multitude of videos online about this topic, and you may find that one of them makes more sense to you than this one. So don't hesitate to check YouTube or Khan Academy or other places to find a video that makes sense to you.